Hello, my name is Zach, and I'm with Mason, Brady, and Ian. We have chosen a tankless water heater as our system. We chose this in order to explain energy conservation in a simple, everyday system. So our proposed system was the tankless water heater. This heats water via convection due to either the combustion of natural gases or an electrical heating element. Tankless water heaters are supplied with an inlet stream of water, and water is then run through a convection heated tubing and exits the system as superheated water supply. Inside of the system is also our heating element, conductive tubing, convection fan, and our fuel supply line. The dimensions listed are what's commonly used in most residential buildings.
In this section, I will go over the different basic types of energy present in our tankless water heater system. Potential energy is present in our system due to the water having to travel throughout the water heater and changing elevation while doing so. However, in our system, the water approximately enters and exits at the same height, so potential energy change is not present in the system. The same can be said about the kinetic energy. Water is moving throughout the water heater with velocity. However, the velocity is constant throughout, meaning it enters and leaves with the same velocity, and so the kinetic energy change is also not present. We have internal energy change, which consists of heat and work. Work in this system is the power input being applied into the system to heat up the water. The power input heats and increases the temperature of the water heater and the water and adds energy. Heat in this system is the overall energy that is being lost to the surrounding environment. In a reversible and adiabatic process, energy in the form of heat would be zero, and all the work applied through the power input would perfectly heat up the water without any heat loss. However, we know that the water heater has a certain efficiency, so we cannot assume that our water heater conducts a reversible and adiabatic process. So heat transfer is known to occur between our system and the surrounding environment. Thus, if we have the following energies within our system, that means we also have enthalpy change, which is the sum of the internal energy change and the product of the pressure and volume.
So what is energy conservation? Energy conservation is the idea that all energy lost by a system is gained by its surroundings, and or the idea that all energy in the universe is constant, as it can never be created or destroyed, just converted into its different various forms. Some examples of simple energy conservation in our system are the transfer of heat energy from heating coils through the tubes and into the water, which is later lost to the environment. Heat put in via convection heating. This heats the water, thus increasing the internal energy. This energy is then dissipated via radiation and convection into the surroundings. There's also mass conservation, as a mass flow in is equal to its mass flow out.
The energy conservation equation for our water heater is going to follow the first law of thermodynamics. It's going to include the assumptions that the water inside the tank is incomprehensible, that the heat capacity is constant, and that the speed velocity of the feed stream and the output stream are the same. The first law of thermodynamics is stated as the change in enthalpy plus 1/2 velocity squared plus height times gravity equals Q plus W. The potential energy term is negligible based on the fact that our system has a relative height change that is very small between the two different streams. The velocity is going to be assumed, as we stated, as the same for the input and output streams, so the kinetic energy terms will also cancel out. Our first law of thermodynamics equation becomes the change in enthalpy equals Q plus W, where Q is defined as the energy lost by the system to the environment, which can be predicted based on the efficiency of the water heater. W is defined as shaft work, the energy put into the system in order to heat the water. In this system, our energy transfers from a couple of different forms to others. This is an open system, and the water in the feed stream is directly heated by coils wrapping the pipes directly inside the water heater, or by a gas heated exchanger heating the pipes in a series as pictured in the diagram. In order to heat the feed water to a higher temperature, electrical energy is converted by passing through the resistant coils, creating thermal energy. In the gas-powered version, the natural gas has a potential energy, which is combusted and turned into thermal energy in order to heat the water as it passes through.
Here's our degrees of freedom. Here we have an equation as we learned in material balance to show our degrees of freedom for our system. After completing, we learned that we have three knowns that need to be specified to fully specify our system, or we have three variables in which we can adjust the outputs of our system. Below is an index of all our variables and their meanings. And then below that, we show that we need three knowns. We need a flow rate and our input and output temperatures, which we can get from geological data, as well as data from how much water we're needing to pull. And then below that, we have our degrees of freedom with our three knowns adding, showing our degrees of freedom of 0. As a proof of concept, we decided to calculate a value of H. With a tankless water heater, our flow rate can vary based off of the demand of the house or unit it is hooked up to. I need to get out of the thing. As a proof of concept, we decided to calculate H. With a tankless water heater, our flow varies based on the demand of the house or system it is hooked up with. And when it's used, hold on, my first random about it. Okay, I'll fix it. As a proof of concept, we decided to calculate H. With a tankless water heater, our flow varies based off of the demand of the house or unit that it is hooked up with. And when in use, the tankless water heater is at steady state. Most tankless water heaters have an efficiency of between 85 and 95%. Using this efficiency and flow rate, we can calculate the H value of our tankless water heater. Tankless water heaters can easily increase water temperature by 27 degrees Celsius. And in Tennessee, the groundwater is about 19.4 degrees Celsius. So we assume that water enters the system at 20 degrees Celsius and leaves at 45 degrees Celsius. We will do our calculations for a bath for 45 degrees Celsius, and most bath faucets fill up about 15.4 liters per second. Assuming we have a slow faucet, our flow rate is 15 liters per minute. And the density of tap water at 45 degrees Celsius is 0.99985 grams per milliliter. Assuming an efficiency of 95%, we've done the calculations below. After our calculations, we found H to be 29.98 kilowatts for heating up a bathtub. Our intensive and extensive properties of our system are as listed below. Our intensive properties are temperature, density, thermal conductivity, specific volume, specific entropy, and specific enthalpy. Our inextensive properties are mass and volume. Our changing properties are temperature and density, as they are proportionally related. As we increase temperature, we decrease our density with water. Our mass and volume also can change due to increasing or decreasing our flow rate. Our unchanging properties are thermal conductivity and specific volume, specific entropy, and specific enthalpy, as they are consistent since no major changes happen in our system. Thank you for your time. Are there any questions?